Hi, my name is Gabriel Londres, and this is my second design and manufacturing project. My project is on 3D printer part cooling ducts. So, project description. This project focuses on designing, testing, and implementing custom part cooling ducts for my Ender 3 3D printer to improve print quality, reduce warping, and enhance cooling efficiency. Standard cooling solutions often provide uneven airflow, leading to poor overhangs and inconsistent bridging. By creating a more effective cooling duct system, this project delivers more precise and uniform airflow around the printed part, improving the printer's overall performance for complex part geometries and higher speed prints. So these are two pictures of the part cooling ducts. The image on the left is the duct by itself with its attachment points, and the image on the right is the duct attached to the tool head along with its 5015 fans slotted in. So, how do these ducts work? Part cooling ducts are essential in directing airflow from the cooling fan towards the freshly extruded filament, improving print quality by rapidly solidifying the layers. So first, the cooling fan, usually mounted near the hot end or on the side of the extruder assembly, pulls in ambient air from your room, and then the duct collects and channels this air, guiding it through an optimized path to the nozzle's output area. Next, standard designs often struggle with directing air precisely, but these custom ducts aim to deliver airflow directly where they need to be and with much greater volumetric uh, flow. And this targeted cooling helps each layer solidify much quicker, which prevents sagging and deformation, especially when printing overhangs, bridges, and sharper corners. So, main printing impacts are on overhangs and bridges, layer adhesion, and surface quality. So, for overhangs and bridges, better cooling allows for more successful bridging and crisper overhangs, since the plastic is basically getting cooled as soon as it exits the nozzle, which allows your printer to basically print in midair, crossing bridges. For layer adhesion, proper cooling ensures the layers fuse well without sagging. And for surface quality, even airflow minimizes defects like blobbing or stringing, which results in much smoother surfaces. So here are a couple more CAD models. The CAD model on the left shows the ducts with the 5015 fans attached to them, and then the images on the right um, show a more detailed image of the ducts and their outlets next to the nozzle. So, how is it made? First, the ducts need to be designed. So the duct is designed in a software like Fusion 360, SolidWorks, or Tinkercad. I personally use Fusion 360. The duct design maximizes airflow to the nozzle and part, minimizing turbulence. So a couple of parameters to consider when designing the ducts. You need to consider nozzle diameter and where the nozzle is, how big the fans you want to use are, and where you want to put them. For example, I use the 5015 radial fans. Um, Compatibility with existing components of the printer, um, such as the tool head, and finally clearance to avoid hitting other parts, such as when bed leveling, you don't want the tool head to bottom out onto the ducts or any frame rails. And then once you have designed your ducts, you want to do CFD simulation on it to test airflow patterns and optimize the duct's shape for even air distribution. And then finally, you prototype your ducts. Version of the design is printed using the same printer to ensure fitment and function. So a couple options for manufacturing materials for these ducts. First you have PLA, then PETG, then ABS. So PLA is very easy to print, and has good dimensional accuracy, and it's a nice finish. The problem with PLA is that it has a very low heat resistance, so it's difficult to use them for ducts which are very close to the hot end. Um, the use case for PLA in this situation is for testing initial prototypes. Um, PTG has a much higher heat resistance than PLA. However, it is slightly more challenging to print due to its high likelihood of stringing. Um, the use case in this scenario is going to be for the material for the final duct because it balances printability with the high durability that these ducts require. And then finally, we have ABS, which has excellent heat resistance and is very durable. However, it's very difficult to print and it requires an enclosure to print. Um, the use case for this is it's ideal for hot environments. So I've chosen PETG plastic to print my ducts. Printing the duct settings, print in 100% infill, 2 millimeter layer height, and supports. Post-processing, remove supports, sand rough edges, and then assembly and installation is simply placing the ducts onto the tool head. So a couple advantages of part cooling ducts. You have much improved print quality. As stated before, it prevents warping and curling as it cools the plastic that gets melted much more consistently. Um, you have better overhang and bridge performance, and very much enhanced print speed. With efficient cooling, you can print at much higher speeds without sacrificing quality. A couple different disadvantages. Um, some of these parts that we print with materials such as PLA can deform over time, um, requiring frequent replacements. Airflow interference, so poorly designed ducts can cool the hot end too much, and this causes issues. And then limited space around the print head can also make it challenging to design. And then finally, impact on fan performance. So if your duct geometry causes back pressure, it might decrease your fan efficiency. Thank you very much for listening.